Good day, everyone. Today I'm going to speak with you about electrophilic addition. So this is one of a two-part series. Okay, you can almost think of an electrophilic addition as a reverse elimination reaction. Now, that said, that doesn't mean that elimination mechanisms can revert back to from being an alkene product to going back to an alkyl halide reactant. That's just to suggest that under different conditions, you'll have a different sort of direction in which things can toggle back and forth. So, for instance, under highly basic conditions around an electrophile or substrate, where an elimination can occur from an alpha carbon getting stripped off and some kind of leaving group going away. You form an alkene, you establish a pi bond, and the rest is history. So we're kind of working in reverse here. So the alkene right here, electron-rich pi bond, is going to coordinate over to a hydrogen that's protic. Okay, so right here where this HBr is, Br minus effectively is the leaving group, so this is going to be going away. Okay, and this is going to be highly protic. So in other words, you need some kind of acid to drive things forward. What's the difference between that and what the conditions are for an elimination? Well, elimination is going to be basic, so it's going to be quite the opposite. Okay, now we have two different options or positions where that hydrogen can end up. It can either end up over here at this carbon and or at the very end or at the terminal carbon. Well, it just so happens that that hydrogen is going to end up at the carbon that has the most hydrogens already, because therefore it's going to have the most stable carbocation. Okay, so if it were to be appear right here and you had that extra hydrogen over here that got misplaced, you would have a less stable carbocation. So in other words, a stable intermediate is really sort of the name of the game. Okay, so once you have a positive charge there, remember this is going to be sp3. That bromo group is going to coordinate, again, going out of the plane of the page or going into the plane of the page and forming a racemic mixture. So this would be an RS mixture. Let me get a pen that doesn't suck. There we go. Okay, so this is going to be RS. Okay, so this rule is simply what is referred to as Markovnikov's rule. So a substituent coordinates the most substituted carbon, i.e. secondary here, with hydrogen, or the protic hydrogen that is, going to the carbon with most hydrogen. So therefore that's going to go on the terminal position there. Again, this carbon is just connected to one other carbon. So in other words, it's going to form a methyl from this alkene, and then on the other side, to satisfy the octet, you're going to have the coordination. Okay, so let's consider a few possibilities here. Again, I'm showing you the different types of carbocation intermediates, which is, just kind of natural for you guys to think about. Which one is going to be more stable? Secondary is more stable, right? So this is going to be primary, kind of a tough sell in terms of being energetically stable. Okay, so some alkenes that are part of a more elaborate pi system, so in other words, something that's cyclic, are going to be more stable than a line structure suggests. So right here, it does look like a cis double bond. However, we typically think of cis double bonds as not being very stable, i.e. somewhat reactive. In this particular case, these pi bonds are going to be constantly circling about. Okay, so in other words, resonance is really keeping these pi electrons from reaching out and kind of going off the ranch, so to speak. So off the reservation, whatever. Okay, so that really is the difference for why there's not so much reactivity with something like a benzene ring or a phenyl ring that you see right here. You need some kind of catalyst in order to let's say have a bromination or some other type of substitution occur. And it would have to be some kind of substitution because aromaticity would have to reestablish because it's more energetically favorable. Okay, so you'll see that next semester in aromatic chemistry and things like that. But really, essentially, what it amounts to is breaking up an electric current, right? So these electrons, just like if they're flowing through the copper wiring or whatever your device you're watching this right now on, right? So some kind of electricity is flowing through there in order to keep everything functioning and for you to view. So it can be literally cut out if you physically separate the two. So if you don't have, that junction right there or that bond right there, then you could have conceivably some kind of, elaborate pi system that's linear. So it wouldn't kind of go in this endless cycle, if you will. Okay. Now moving on to actual reactivity, let's turn to kinetics for a minute and just think about some slower to faster types of intermediates that would, kind of push along these electrophilic additions. Okay, so we have compounds A, B, C, and D here. Excuse me, I just ate dinner. So we have tetrasubstituted, we have tetrasubstituted here, and we have not substituted at all, ethene, and then we have a trans sort of linear alkene species here that's disubstituted. Okay, so if we really think in terms of in terms of reactivity and things of that nature, we really tend to think of something that's more open as being more unstable, right? There's nothing to really stabilize and keep those pi bonds kind of scrunched in there like you see with A and B. Now, remember that this has to kind of, this pi bond has to kind of lend itself out to coordinate to that hydrogen. So that's always going to be the first step. But what the name of the game is here in terms of intermediates is trying to establish which one is going to be most stable, right? So in other words, if you were to say tack on a hydrogen here, let's just say, just for generic purposes, it's going to be H plus. Now you have a positive charge about, a primary ethyl carbocation. So that's going to be really, in other words, the slowest kind of mechanism, because this is going to be so unstable that that hydrogen will be more or less rejected. Okay. And then we have our next. So, we have now, we would form some kind of secondary. Let's just put A for acid to make sure it's just generic. Okay, so it picks up that hydrogen there. And either way you slice it, you're going to have a secondary carbocation. Let's say we just put it on the bottom there. So that new hydrogen's over there, up top. Okay. So either way you look at it, it's not going to be very stable relative to what you see over here. You're going to get tertiary carbocations at either side. Now this one is a little bit of a different story from A because it's going to be resonance stabilized if you have phenyl rings right there, and it can resonate about each ring. Okay, so in other words, this is going to be the most reactive, followed by this, D, and then C. So C is going to be least reactive, followed by D, followed by A, followed by B. Again, resonance stabilized is really going to sort of be the edge here between A and B. Okay, so again, kinetics doesn't necessarily mean that things won't happen. We're just talking about a matter of when, not if. Okay, so how many isomers can be conjugated or what have you? And problem 11.25, page 596. So these are all different types of isomers, constitutional isomers of C5H8. Okay, so you're going to have two IHD. Now, the manual actually gives you a slew of different assortments of cyclic compounds. We're just going to go with these just to show what you would do at lower temperature versus higher temperature. If you recall back in chapter 9, you'll recall that we were talking about kinetic control over thermodynamic control. So kinetic control is something that's going to form the fastest, right, with the least amount of energy input, i.e. heat. Okay, so if we were to do this particular low temperature setting, and we would have this electrophilic addition, this hydrogen would go at the terminal end here, and then you would have a carbocation, and then that Cl- would coordinate right there. So the product would look like this. And again, you would have a racemic mixture, because this is stereo. This can have stereoisomers at this particular center. And you would also have a mixture of R and S, right? So remember, if you have that carbocation as an intermediate, it's going to be sp2 hybridized 50-50 shot either way. Now at higher temperature, remember that if things are going to be sp2 on this carbon from a hydrogen being attached, it can actually conjugate very well with this double bond. So this is going to be a more elaborate sp2 system as a result. So, the higher temperature that you put in, or the higher heat energy that you put in, the more likely that double bond or pi bond is going to flip over onto the other side. So you're actually going to see this kind of product. Is it any different from what's up top? Nope. Okay. Now, on the other end here, you're probably going to see the same sort of thing. Again, this is going to be cis as opposed to trans above on the second one. So you're really going to see kind of the same phenomenon here. The only difference is when you do the low temperature, you're going to keep that cis configuration that you see right here. So in other words, you'll see this at low temperature. Remember, at high temperature, you're probably going to pop this bond off or have some kind of rotation from, an anti-bonding molecular orbital, breaking up that pi bond electron cloud that overlaps, and then things are going to flip to a more thermodynamically stable product. So, in other words, don't forget your R and S mixture here. So again, this squiggly line is just to represent a mixture of R and S. Okay, so so pretty much the same thing you will see from that previous example, or with the trans isomer. Okay, so now it's a little bit of a different story. So this one's going to be at low temp. Let's just say it's at low temp. Okay. So you're going to see the same thing like you saw before. However, it's not going to be conjugated. I keep on missing that squiggly line. Shame on me. But you're going to have that, just assume this is one equivalent or what have you. And you'll just have that, excuse me, vinyl group on the opposite of it. Okay. So why don't you take a look at problem 11.30 on your own time and see how that changes when you apply heat. So remember that you can have some kind of carbocation rearrangement if there's some hydrogens around or methyl groups, whatever. Okay. Hint, hint. Okay, so onto a product species, like say an alcohol or an acid that you want to amend to an alkene and, establish some sigma bonds. Okay, so for this particular instance, the proton source is going to be H2SO4. You would probably use this mole to mole right? Or maybe a little bit of a slight excess, depends on what the kinetics are. But so if we were to do our mechanism here, we're going to pick up hydrogen from that sulfuric acid source. Okay, so what we want to do here is actually form a more stable carbocation here, which is going to be tertiary. Now, water isn't the world's greatest nucleophile, but for these kinds of conditions, we can accept that. Okay. And this is not going to be stereospecific, so we don't have to sweat that. Okay. Now, then we have water, which is also going to act as a base here. And then we have a stable species, which is going to lead to, back over here, and that is going to be your addition or hydration, in other words. So this is going to be hydration reaction. Okay, so now you're literally adding water by using an acid catalyst. Okay. All right, so the next step, if you didn't use a catalyst, something like this might take forever. So it's really just a precaution, I guess, if you will. So remember, you're going to generate H3O from this last step. Okay, next example here. So a 5-membered ring now. Tri-substituted alkene once again. We got a weak acid. We also have H2SO4, which is really going to be the protic species. Okay, so which one of these two is going to be the stronger acid? H2SO4. All you have to do is look at your pKa table. I should tell you. All right, so, whoops. Now I have a hydrogen here, positive charge over here. Do we need to have a methyl or a hydride shift? Nope, not at all. It's most stable where it is right now. Okay, so let's say if we have a weakly nucleophilic acetic acid, positive charge is going to remain there. Okay, and then this is going to be even more acidic now. So conjugate base of H2SO4 is just going to pick that hydrogen up. This is going to be way too acidic. Take it back, and then you're going to have an ester formation right there about that junction. Okay. The third example, why don't you guys give it a shot? So this is going to be a tri-substituted alkene, but also pay attention to the fact that you're going to have two different carbon branches off of this bottom carbon there. Excuse me, so pay attention to that, and I'll give you a minute or two to work on it. All right, so for this next mechanism, let's just quickly pick up this H. All right, we'll just assume it's from that acid, stronger acid than this. So that hydrogen again is going to go to the carbon with the least amount of hydrogens. Okay. So in other words, you have an ethyl group right here, you have a positive charge, and then your weak nuke. In other words, ethanol is going to come coordinating in. And then you're not going to have a optically active product, because you have an ethyl group here, ethyl group here. Okay, so in other words, you'll really have CH3 here. And then you're going to have a second ethanol group that's going to act as a base. Pluck that hydrogen off. Boom. So in other words, you're going to get an ether compound that's going to look like this. Okay. Righty. So is this just applicable to alkenes? Not at all. There's also alkynes, so you can double the pi bonds, double the reactivity. So that's just for halides. This may take a few days, but if you have everything in excess, you can actually attach things on twofold. So it means two equivalents of HBr are going to amend to those two pi bonds and have everything fully quote-unquote saturated. So and sp3. Now the question is where are these bromines going to go? Are they going to go here, or are they going to go here? Because you think to yourself, well, both of these are going to be singly bound to something else and sp hybridized. Well, here's the deal. The fact that this is going to be electron withdrawing and have some kind of conjugation in the intermediates, right? The positive charge is going to be more stabilized over here because it's going to have some resonating effect with that phenyl ring. So, in other words, you're going to see this product as a result. So a dibromo species like so. Let me see if 1, 2, 3, 1, 2, 3. Okay, we're good. Yeah, so in other words, you're tacking on two equivalents of HBr onto that triple bond to have two sp3 carbons as a result. So this isn't going to be the same effect for water. Again, if you're going to be using H2SO4, you're going to have your water act as a nuke, and it's going to show up right here, just alpha to the ring. Now, what we recall from, I believe it's either chapter 6 or chapter 7, we're going to have an enol tautomer here, which is going to be less thermodynamically stable than its keto form. So we're going to be under a protic system, so protons are going to be passed hither and thither, and you will get I drew that really wrong. Okay, so same count of carbons here, 1, 2, 3. And this shouldn't be cis. This should actually be trans. Doesn't really matter because this is just going to be an intermediate anyway. You just put this in brackets or something. But remember that the ketone is going to be a more stable form, so it's going to go in this direction. Let me redraw that because it looks super ugly. All right, here we go. There, that's what it looks like when it's sober. There we go. Okay, so moving on. So effectively, if you want to generate some kind of stable ketone like this, this is really sort of your best bet up to this point. So taking a triply bound alkene, and it's not terminal, so that's really the key. It can be terminal as well if you're using these kind of conditions, but you can have some other safeguards, as we'll see later. So here's the next page, sort of serves as a worksheet for kind of summarizing what we've talked about in this particular lecture. Okay, so first thing we're going to do here this is problem 11.29 on page 596, so this is just a mechanism review. So the species picks up its hydrogen. Okay, so where will the carbocation end up? Near the lone pairs, right? So this can resonate down. Okay, so in other words, this is going to be the major resonance contributor because you have a full octet here. Remember, there's that extra hydrogen sticking out. Okay, and so you have a full octet here. You have a full octet about that oxygen, so everything's good. All right, so now that if you have that Cl minus, that is quote unquote the leaving group from the first step or first coordination, now that can come in and poop, knock over those electrons back to oxygen, and now you have Cl directly next to your oxygen. Okay, so here's an intramolecular ether formation, so you can see the transformation already. I'm just going to kind of show you the magic in terms of how this transformation occurs. So per Markov-Nikov's rule, this is going to pick up a hydrogen okay, so you have a methyl group which is exactly what you see right here. Okay, so let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so this can self-cyclize, forming a 5-membered ring, which isn't a tough sell at all. So now we have a 5-membered ring, sort of a tetrahydrofuran derivative, protonated ether, which, you know, if there's some other type of OH species like what you see right here, so a second equivalent of the substrate rather, or you know, you could use that base, conjugate base of HSO. Let's see, SO2, and then, so scratch that. Put a negative charge here. This is going to pick up that hydrogen. Okay. Pretty straightforward. All right, next problem, 11.40 on page 597. Just predict the substrate and then also the mechanism to form this kind of ketone. So really all you need to do is envision a triple bond that had previously existed there. So that would be right there in between these two carbons. And this would be a linear compound. Of course, you would use water with H2SO4. You're not going to get any squirrely rearrangements with this. So, all right. So let's just put a hydrogen or acid right there. Excuse me. So now we have a protonated intermediate. Okay. So this will be most stable. Okay, so again, just using water, H2SO4, acid catalyzed hydration. That water molecule is going to amend here, coordinate. And then your acidic conditions, you're going to be following positive charge. Okay, so we're going to form our unstable. I'll just shorthand this. Enol intermediate. Again, very little going in this direction, almost 100% going in this direction to form a more stable ketone form or keto form. Okay, one last example, this time involving synthesis. So if you haven't noticed by now, I'm kind of gradually getting you guys more into the kind of mindset of synthetic analysis and synthetic approach. So this is kind of marrying chapter 10 with chapter 11 stuff. Because, again, this is all going to be stuff you're going to see on your third exam. So, having two equivalents of NaNH2 is going to eliminate everything and strip off this chloro group, so you're going to have an alkene. But remember, it's going to be in its conjugate base form because this is really strong. And then you're going to have water to protonate it. So, what you're going to see for your first step is this. Then you would use NH2 to strip off this hydrogen. Again, kind of robbing Peter to pay Paul here. Then you're going to pop this epoxide open, right? And then just acidify that with water. So that's going to look like this beast right here. So 1, 2, 3, 4 carbons hanging off of that phenyl ring. Treat that with PBr3. You're going to change the primary alcohol to a primary alkyl halide. Okay, so now you're going to use water, and then in the presence of tosic acid and I don't know if I wrote that correctly, but trifluoro. Hell, I don't know exactly what that acid is off the top of my head, but nonetheless, it's going to be a strong acid to catalyze the reaction. Okay, this is going to be just acid catalyzed hydration. Now, it's not going to substitute where that bromo group is, right? Because, again, proton transfer is going to happen faster, and it's going to actually, one of the pi bonds is actually going to be perpendicular to this whole pi complex here. So remember, it's going to be, one of these is going to be conjugated to this phenyl ring that you see right here. So it's going to reach out, pick up one of these protic hydrogens, and then effectively you're going to form a ketone, like I've done a couple times before now. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And that bromo group's still there. Okay, so that cyano group is going to do an SN2 and substitute that bromine. So then you're just left with this product. Okay. So that pretty much wraps it up for the first half of electrophilic addition. If you have any questions, just come tag along during Teams for office hours, and we'll get you straightened out. Okay. In the meantime, I'll have this posted, and then right after that, I'll have electrophilic addition 2 set up for you. So this next phase is really going to be looking at 3-membered ring products and or intermediates. All right.